5.7 numerical integration. We're going to start with, that's at the beginning of this section, absolute error, where it's the absolute value of the computed value minus the exact value. And this gives us a percentage of error between the two computations. The thing is, I will come back to an example of this, but I wanted to go ahead and get this out of the way. Computed is, remember, our rectangular approximation, and what we're going to be talking about in this section, are approximations. And their exact values that we're going to use for x are coming from your calculator, because the calculator has a slightly more precise algorithms in your calculator. So we'll come back to this absolute error. But my big thing I want to talk about now is the book talks about the midpoint rule. And for this case, I'm not going to do anything very much different than using your calculator program we put in for the midpoint rectangular approximation method. I'm not going to go any different from there. So I have, for example, number 11. They give us the integration of a function, and yes, we can use fundamental theorem of calculus for this and find exact values. But they want us to use the midpoint rule when our subintervals are 1, 2, and 4. So I went ahead and I did that. I worked it out by hand. So I did all these computations using our midpoint rules, finding the area for when it was one rectangle. Here's the area with one rectangle. Here's the area with two sub-intervals or two rectangles. And then I did it again, the area with 4 rectangles. So by hand computations. And then we can always go ahead and, oops, I'm going to come back to that one in a second. We can always go ahead and use our program in our calculator for left, right, and midpoint rectangular approximation method. And for that is what I did here. I will be coming back to this problem in a minute. So if we're moving on, there might be a slightly better one. We call it the trapezoidal rule. So if I have, for example, a graph that looks like this, we know left rectangular approximation could be over or under. We know right rectangular approximation could be over or under. And then we said, okay, well, it looks like a midpoint rectangular approximation is pretty good. If we did not have in our calculator a program that already did the midpoint rectangular approximation, and it was easy to calculate mid or left and right, we can have another method. So I'm going to show you here on this slide the two different ways we can calculate. Roughly, we can just say we're going to add the two left and right rectangular approximations and divide by 2. And that's the same thing as saying it's equivalent to trapezoidal rule. We are going to do an example using this. But if we look at the one above, where t equals h divided by 2, where h is our delta x. So we could rewrite this in many different ways. So I'm going to actually simplify this. Notice it's our delta x divided by 2, and our first and last values are by themselves. So it's really going to, those are going to be divided by 2. And then we have that all the terms in between are multiplied by 2. And it's all going to be multiplied by delta x. So another way of rewriting this trapezoidal approximation is delta x times, we're going to do 1/2 of the first rectangle. Oops. Let's put rectangle. And then sub 1. And then everything else is going to be, we'll do r sub 2 dot 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 plus whatever the last one will be. And I forgot to squeeze in my 1/2. Like this. So this is a much easier way of remembering the trapezoidal rule. It's always going to be your delta x times half of what our first and last values of the rectangles are that are summed up with the rest of the inside rectangles. So this is our trapezoidal rule. So I want to go ahead and do an example of that. All right, so if I go ahead, I'm going to say this would be number 18. But really, it's going back to, number 18 is going back to number 14 that we had. And that we had this problem. Oops, my dx is not in the exponent. And if we use the left and right rectangular approximation and using the trapezoidal rule, and we see here we get 0.633. So in this trapezoidal rule, I'm taking the left rectangular approximation plus the right rectangular approximation and dividing by 2. If I go back and look at what I had written down for this one, I had 0.63, if we're rounding to 3 places, 0.632. But when we were doing the trapezoidal rule, I had 0.633. So there is a margin of error, even if we then, between our two methods, our midpoint rectangular and our trapezoidal rule. And then there would be an error, absolute error, between finding the exact and this approximation. If I want to go ahead and try to do another one, from information. This is where trapezoidal rule comes in really into play, even on the AP testing, is when we're given a chart. So I'm going to pause and write in my chart. Okay, for this problem, number 27, we have an hourly temperature data for Boulder, Colorado over a 12-hour period on the day of January as shown in the bar chart. And then it says, assume that these data are taken from a continuous temperature function, T of T. The average temperature over the 12-hour period is T bar equals 1/12 times the integral from 0 to 12 of T of T. So what we want to do is we're going to go ahead and try to do the trapezoidal rule using data. So from here, I'm going to say that this should equal 1/12 times, and I'm going to have, and it might be easier to do it this way, or we can do it the shortcut or the long way. The delta x, which is, I can see my delta x here is equal to 1 because all my intervals are going by 1. So I'm going to be multiplying my delta x by 1/2, and this is the case where I'm going to leave that delta x over the 2 on the outside. I'm going to go ahead, if I want to do it this way, I'm going to say I'm going to leave the first and the last. So this is my first value and this is my last value on this chart alone. And then I'm going to say, okay, plus 2 times the rest of the data points inside my chart. So when I have my data point for 1, 2, and then I'm going to go ahead and try to squeeze all these in here. 45, 48, 52, 54, 61, 62, 63, 63, 59. So this is the one where it was like the first example of that, for the trapezoidal rule that we had. Now, if you notice that, we could have just divided this one by half, this one by half, and then not have to worry about 2 times the rest of the data points. However you want to do it is fine, as long as you remember what you're doing. So then when you go ahead and calculate all this up, you're going to, obviously, order of operations. I'm going to do summation here. I divide it by half, and then I can divide by 12 again. So that, or multiply by 12, multiply 1/12, or you can go ahead and basically do the summation and divide by 24. However you want to think of it mathematically is fine, as long as you do it mathematically correct. So we should have an approximation for the trapezoidal rule of an area of 54.5 degrees. So that's what we should have over this 12-hour period. All right, I'm going to do another one, approximating integrals. Number 29, a curling iron is plugged into an outlet at time t equals 0. Its temperature, capital T, in degrees Fahrenheit, is assumed to be a continuous function that is strictly increasing and concave down, and is given a various time in seconds in this table that I'm going to write out. It wants us to approximate in 3 different ways, using left Riemann sum, right Riemann sum, and the trapezoidal rule. So we can go ahead, I'm going to fill in this chart. All right, so here's the biggest thing about the difference between 27 and 29. As we're given the same kind of situation, I do not have a constant delta x. The widths are not partitioned equally. So I'm going to have here, and I'm going to say delta t sub 1. So from these first two, I see that my width is 20. But my delta t sub 2 has a width of 25. My delta t sub 3 is 15. My delta t sub 4, it looks like it's 30. Delta t sub 5, 20, and delta t sub 6 is 10. So all of my widths for my rectangles are going to be different. So I'm going to have to slowly do a different application of this one. In this case, though, we're going to say the area is going to be approximately to 120, 1 over 120 times, and this is where I'm going to do this for the trapezoidal rule. They said use left. So here's my left rectangle approximation. I'm going to be starting from my left values of my chart. I have a height of 70 but a width of 20, plus a height of 30 times a width of 25, a height of 200 times a width of 15, height of 229 times a width of 30, plus a height of 311 times a width of 20, plus a height of 355 times a width of 10. So notice for left rectangular approximation, I start with the left number. I go 1, 2, 3, 4, 5, 6. I only have 6 widths. That's all I can do. So notice that for my height, my final T of 375 is not in my left rectangular approximation. I can go ahead and do my approximation from here, and I should get this answer. If I want to do the right rectangular approximation, same thing. I'm now going to go ahead and with my right rectangular, I see I'm going to start from the other side of the equation. So I have a height of 130 times my width of 20. I'm going to have the height of 200 times 25. That's 239 times 15, 311 times 30, 355 times 20, and 375 times a width of 10. So now I'm going to be starting with this using my 6 width, the delta t sub 6, and I'm going to be working 6 rectangulars this way. And then I have that value. So if I go ahead and figure out my calculation, I'm 261.375. So then they said the last thing is go ahead and do the trapezoidal rule for on this one. So my area should be 1 over 120 times, and I'm going to go ahead and say 1/2 times that first one, but I got to average now my left and right midpoint, or left and right. So now we're bringing in that midpoint rule along with the trapezoidal rule. So here's my first 2 heights, and I'm going to multiply it by that first delta t sub 1. Then I have that, I'm going to go ahead and say my have 1/2 times the 130 plus 200, the next set of 2 heights, and that's going to multiply by my t sub 2. And if I keep writing this out, and I should have my 6 trapezoid areas, and this technically is the area of a trapezoid. 1/2 the two bases, or the bases times the height. In this case, remember it's on its side. So that's why I have the 1/2 along this whole thing. It's following a slightly different formula. I'm sorry, I'm squeezing all this in here. So all of my trapezoidal areas are getting added together and then divided by the 1/120. So using basically geometry in this trapezoidal rule, calculating each one, we see we get 233.146. That is definitely between 204 and 261. We're assuming then that's the better approximation. All right, the last one I want to talk about is number 23, going back to that error that we had. If I'm given this equation, and the book tells us the exact value of it, they calculated it for us. They want us to go ahead and make a grid using the midpoint rule, the trapezoidal rule, and then find both errors, the midpoint error and the trapezoidal error, when we have n is equal to 4, 8, 16, and 32. So they want you to make a chart like this. And this is where you're going to calculate each thing here. First, for this one example, using my program, I had that for my midpoints. Using trapezoidal rule, I had 1.408, and I can't read my writing, something like that. So this is your, when you go to do the errors, remember for this one, we're going to use t minus the exact. So it's going to be, in this case, the 1.4, the absolute value of the 1.48065 minus the 3/2 that they gave us, and that's your value here. So for the last one, for the error, it's just a lot of plug and chug and calculating the absolute value of your approximation to their given exact. And that's all we're going to do with the errors that we want to find here.